should be pressed up.
Huh?
You can press this.
So I think it's time to begin our session, and hopefully others will drift in over the next 5 minutes or so. Our first speaker of the afternoon is Professor Abhishek Dhar from ICTS Bangalore. Please, Abhishek.
Yeah, thanks.
We are 1 minute ahead.
Oh,
Oh, it's not.
Not
30.
yet.
Okay.
No, it is.
So you should give the introduction.
Yeah, I'll get 1 minute extra. But yeah, okay. Okay, so let me start again by thanking Sanjib for organizing this really nice meeting. It's always great to be in RI. Yeah, actually, I just remembered about 25 years back, I gave my first talk here, like as a job applicant. Okay, so yeah. Okay, so this will be kind of a relaxed talk after lunch talk. So I'll talk about hydrodynamics of hardcore active lattice gas, and this is work done with two really brilliant students, Ritik Mukherjee at ICTS and Shomabrata Shah at TFM Mumbai, and of course Sanjib and Trideep. Okay, so so actually a lot of the introduction to the talk has been given already by various speakers who have talked about motivation of why we study active materials, and also Sanjay's talk is very closely connected to what I'll talk about. Okay, so it's not moving. It's not moving. Maybe yeah, it's not moving. Okay, maybe now it will move. Yeah, okay. Okay, so this is the outline of the talk. So basically, I'll talk about a lattice model of interacting run and tumble particles. Mostly, I'll talk about one dimensions. So basically, it's the interaction is just exclusion, and we instead of a 1D lattice, we talk of a two-lane model, and I'll explain why. And basically, I'll present there's a hydrodynamic theory and comparisons with microscopics. And this model shows a mobility-induced phase segregation. So I'll show that, even though it's a 1D model. And then I'll talk about some results from fluctuating hydrodynamics, results in higher dimensions, and the reason why we work with this ladder model and not a strictly 1D model. Okay, so first I should say that there's been actually a lot of earlier work on this model. I mean, what we study is a kind of a variation of a lot of earlier work. So this, I think, this was one of the first studies, 2018, where they studied this lattice model with interactions. So this is basically run and tumble particles. So run and tumble particles at the single level, one knows if there's a particle which can have either been a plus state or a minus state. If it's in a plus state, it goes preferentially, it does a biased random walk in the plus direction. If it's in a minus state, it does a biased random walk in the negative direction. And there's some flipping rate between this plus and minus states, right? That's the run and tumble particle. And then you put this on the lattice and then include interactions. So that's the model. Okay, so this is the model studied by these people. So here what you see is that the plus and minus particles. So it's two species of particles. And then there's a rate at which they can interchange. This is gamma divided by some length square. Okay, so you have to scale the rates in some way. So this is the rate at which tumbling rate, right, between particles. Then there's a diffusion, just a normal diffusion of particles, and then there's a bias. The plus particles are biased to this direction, and minus particles are biased to this direction. Okay, so one of the ingredients in this model, which is really essential, is that if you have plus minus particles, then this exchange is allowed. Okay, so this is kind of a crucial step. You need to allow this exchange of plus minus particles. Okay, so normally you might think that since if there's exclusion, they shouldn't be allowed to jump on top of each other, but this step is also included. Okay, so these are the rates. And in this, like what was interesting is that they provided a microscopic derivation of hydrodynamics in this sort of active model. And one of the interesting things was that they demonstrated transition to this. So in the parameter regime, there's you see a transition to this phase segregation state. Okay, so there have been a lot of studies. In particular, these people have looked at fluctuating hydrodynamics and then current fluctuations and so on. And PK here has studied a slightly different version where he showed actually that with that change, you can do some mapping to this zero range process, and then they showed that there's no MIPS in this particular model. Okay, so there's been a lot of earlier studies. So our main motivation was to sort of remove this step. Okay, so I mean, this looks like a bit artificial step to include. Now, if you remove this step, then what you find is that in the microscopic model, you don't see any MIPS anymore. It's always homogeneous. And also, you see that hydrodynamics kind of fails. Okay. So this is one sort of interesting question, like why is this term so important? And there are sort of various possibilities which I'll discuss at the end. So what we decided is that we don't include this term, but we think of a physical system where, like, it's an arrow channel where particles can kind of get across each other, right? So that's why we study a two-lane model, and we don't have such a process. But particles can go between the lanes, and of course, then they can overtake each other, right? So indirectly, we allow exchange, but in a more physical way. Okay, so this model, what we'll show is that actually the hydrodynamic equations change quite a lot, but many of the phenomenology remains the same. Okay, so let me define the model more precisely now. So we have two lanes. And on each lane, you can have these plus and minus particles. Plus are red and minuses are blue. And there's a plus can go to minus with some rate, which is gamma divided by some length square, which is basically when we go to the hydrodynamic scale, we need some coarse graining length scale. So you can think of this as that length scale. Okay. So this tumbling rate is given by this parameter gamma by L square. Then plus particles hop, there's a bias to the right, so d plus lambda by 2L, and to the left d minus lambda by 2L, and minus particles are preferentially do a walk to the left. Okay, and the bias is kind of, again, has a 1 by L, so it's a very weak bias. It's like WASEP, weak asymmetric exclusion process. So this we need to get the proper hydrodynamics. Okay, so this is the model, and then there is this exchange rate between the two lanes, which is epsilon. Okay. Okay, so I think I've defined everything. So there are two lanes, and there are two species of particles, right movers and right movers. One or no particle at each side, that's exclusion, and this is the dynamics, right? And this is the tumbling rate, and there's interlane hopping. Okay, so now in this model, you can see that there's just one, yeah. Epsilon, we don't scale, yeah. It can, we want it to be quite large. Yeah, we just want to, eventually the particle should be able to get across each other. Right? Yeah, so that's the motivation. Okay, so I hope the model is clear. Any questions? Sorry? Okay. Okay, so this is the notation. I mean, this denotes the number of, so sigma is plus minus 1, that's the species, and I is 1, 2 are the two lanes, and x is the position of the particle, right? So this basically specifies the state of the system. Okay, so now if we make this exchange hopping very large, then you can imagine that these two sides will equilibrate kind of very quickly. So you might sort of make this approximation that these two sides they have almost the same density, and then I won't have these two labels 1 and 2. I'll just have this label nx, right? Okay, so this is one. Eventually, we'll make this approximation, but the idea of introducing a large epsilon is basically this. Okay. Now, to write the hydrodynamics, we need some assumption for the steady state of this system, and we'll basically assume that, okay, so we don't know the exact steady state for this model. So we'll assume there's a product measure, and then we'll replace 2-point correlations by product of 1-point correlations. Okay, so these are the usual assumptions one makes while deriving hydrodynamics. So it's like a local equilibrium assumption and also product measures. Okay, so then we need to look at basically the variable in the hydrodynamics will be the density of plus particles at site X and density of minus particles. And then the other interesting variables are the total density, which is just the sum of the two densities. And then this is like a magnetization variable, the difference between the up and minus. Yeah. Total number of, this is same. Yeah, I will get nonlinear, but the conservation is strictly because I write it in a divergence form. It's exactly what I do in reshape or usual exclusion process, right? I mean, that's okay, so this will be the two important fields, the density and the polarization or magnetization, whatever. So we'll try to write, yeah. Yeah, we have measured and they are really small. Like it's, sorry, it's scales. So this correction will be like 1 over L, 1 over root L, I think, 1 over root L. Right, yeah. Okay. Maybe, yeah, maybe 1 over L, right, yeah.
Go ahead.
Okay, sorry. There's a watch? No. Okay, actually I should go slow because I have a lot of time. Okay, so actually if one can write exact equations, so in principle there are 4 fields. On the 2 lanes there are positive and negative particles, so I have 4 fields, and these would be the exact equations that one can write for the density. So it basically implies that, like if I look at the bond between x minus 1 and x, there's some current, and then between x and x plus 1 there's a current. So I just take the difference of these 2 currents, and then, sorry, this is, something is missing. Okay, sorry, this one, there's some missing, there's some typo here. So this is the sort of tumbling rate, which just depends on the local density, right? It should be minus gamma times just the density at that site. And this is the exchange between the 2 lanes. Okay, so this is one can write this kind of exact equation. And then we see that this 1-point equation involves 2-point correlations. And then we make this approximation of a product measure. So we'll break this into 2-point correlations. And then we also make this assumption that because the hopping between the lanes is very high, so this is almost equal, and therefore we can replace these 2 densities by a single variable, right? So the 2 densities on the 2 lanes are almost equal, so I can just look at 1 density field. Okay, so this leads us to then the hydrodynamic equations for these 2 density fields. And these are the final equations that we get. Okay, so if you look at this equation, so this everything is in the form of a divergence, right? So that's what, except for these are just the tumbling rates. But this one is, it comes from the hopping, and this is basically the current from x to x plus 1. Okay, so this whole thing is the current from x to x plus 1, and you have divergence of this current. Okay, so this is occupation of site x, and this is the probability that the next site is empty, and similarly the reverse way, and then you have these rates. Okay, so these equations are easy to understand, and then we take the sort of diffusive scaling limit where time scales as tau by L square and x scales as capital X by L. So these are the kind of small t and small x are the macroscopic space-time scales. And then this equation basically simplifies to this form, okay. So I have done some expansions in rho x plus 1 and so on, and then we get this equation. Okay, so I should say that, I mean, if we do this for reshape, then, I mean, we'll get the Burgers equation. And, I mean, there's a more rigorous way of deriving the Burgers equation, but this kind of phenomenological method where we are just doing some expansions actually gives the correct result for WASEP. Yeah. Epsilon disappeared because of this, right? I said so. If you right, then it just goes away. No, finally, of course, yeah, I could have got 4 equations, right? Yeah, yeah. But when I add the 2, I'll just get 2 equations, right? Yeah. But yeah, we want this to like fast exchange between here so that the 2 lanes equilibrate quickly. Okay, so so these are the equations. Now, if we add these 2 equations, we get an equation for the density. If we subtract, we get an equation for the magnetization. So after doing that, and then if we just go to dimensionless variables in both space and time, so makes both space and time dimensionless, then it turns out that the final equation has just one free parameter, which is this Peclet number, and otherwise there's no other parameter. Okay. So the first equation, I mean, physically it's clear. There's the density, there's some diffusion, and then there's a drift where the drift velocity kind of depends on the net here, right? Velocity, yeah.
How is it different from that in
If you look at these equations, the first equation is the same. The second equation is different. Like the form is, I think, like here is just del x square m, and then this term is there, but this is not there. Okay, so there's some difference in details. Okay, the first equation is exactly the same. Okay, so yeah, so this there's a drift, and of course this just says exclusion, and then the magnetization has okay. So part of it is like conservative, and then there's this non-conservative because the magnetization will eventually decay, right? Because of it's a non-conserved process. So okay, so there are 2 fields, one conservative and non-conservative. Okay, and this Peclet number is basically so this is like a velocity, drift velocity. And then this is the diffusion constant and tumbling rate. Okay, so this is some. It just compares the activity to the like the regular diffusion. Okay, so it's kind of a strength of activity in the model. Okay, and so there are so apart from Peclet number, of course, the other parameter that will determine things is the overall density of density, right? So basically, there are 2 parameters: Peclet number and density. Any questions? Okay. Okay, so I'll just show some movies. So supposing I start with some initial conditions of the some distribution of the density of particles and the magnetization of particles, and evolve it with this hydrodynamic equations. And I also run the microscopic simulation. Okay, how well does hydrodynamics capture the microscopic evolution? Okay, I mean, yeah, so let me just show. So the first one is in a sort of low density parameter regime, and this is what you see. So initially we start with some kind of a Gaussian profile, and the solid line is the hydrodynamics, and the liquid, and sorry, not liquid, the points are the simulation, microscopy, okay. So you can see almost right from the beginning, I mean, they completely, so it captures the evolution at almost all times, okay. So this is in a kind of high density phase where we start with some initial condition, and eventually, so at low densities it went to a homogeneous phase, but at high densities it goes to a sort of, so this is the density profile, the black line. And the red line is, this one is, I think that's positive particles, and these are the negative particles, okay. So, so you can see that I mean, so in this case, the positive and negative is uniform, and so the magnetization vanishes in the homogeneous phase. But in this, segregated phase, you see that the positive and negative particles have different profiles, so there's a net magnetization in the system. Okay, and what is really quite very nice is that the hydrodynamics and microscopics, I mean, they agree quite well, I mean, at almost all times. Okay.
What are the lines?
Lines are from hydrodynamics, the points are from microscopic simulations.
There is some mismatch.
Yeah, I mean, this, okay, this one was, okay, so yeah, in many cases the agreement is much better. This one, okay, yeah, here you see some bit of mismatch, but, okay, I don't think it plays. So the only, in the parameters are these flipping rates and all, right? So there's almost no. Yeah. Yeah, exactly the same parameters. I mean, finally, only the Peckley number matters. So in the microscopics, you can put parameters in some way, and then this is what we see. Yeah, so only in the hydrodynamic equations are, of course, there's no dimension. But you can, in the microscopics, you can put whatever your dimensional. Finally, you can plot like non-dimensionalized quantities.
So a lot of times it becomes homogeneous.
In this phase, in the low density, it's homogeneous, but here, no, it just stays like that. This phase, this is the MIPS phase, right? Yeah. So you have high density and a low density phase coexisting. Okay, and so you can see that the plus particles are kind of high in this region, and the minus particles are high in this region. So they're kind of, I mean, they're pushing the thing. So the diffusion terms is trying to make it homogeneous, but the magnetization tries to like sort of. This is periodic boundary conditions, yeah. So the shock actually can develop anywhere. I mean, this phase can develop anywhere on the, depends on slightly. Yeah, it depends kind of on the initial conditions. Right? Small? Very small L? Oh, what is the length? I can't remember. This is 1 year back. I think it was, I think for a lattice of like maybe 4,000. Yeah. The system size was, I think, around 4,000 or something. Big, yeah. This might be this, yeah, this particular simulation I don't remember. But like afterwards, I'll show even better agreement.
Questions at the end, maybe, I mean, unless there's a very urgent question in the middle, yeah. Otherwise, don't disrupt Abhishek's.
Okay. Yeah, I have time. I mean, yeah, it's fine. Yeah. Yeah, I think otherwise I won't have. Yeah. Okay, so this is something maybe which satisfies Purnavrata more. So here, I mean, so this is again the MIPS phase where I plot both the simulation and the solid lines at the hydrodynamics. Okay, at different times. Okay, so you can see, I mean, right up to the steady state it matches. Here, I mean, okay, the steady state is still, okay, so the magnetization actually reaches maybe the steady state. Okay, I don't know why it's, the steady state in this case is this profile. The simulation till here it agrees, and then, okay, I think we didn't do the microscopics. You have to do long enough to see the steady state. Right, yeah, that also is there, okay. Okay, and this is in the homogeneous phase where eventually, so you can see that agreement, even at early times, is quite good, right, between simulation and microscopics. Okay. Okay, so now we have, okay, so from simulations we see that there is a, depending on parameters, there is a homogeneous phase and MIPS phase. And so then question is, okay, so like how can we understand it from this equation? So basically in the steady state, we should, I mean, one can easily see that if I take rho equal to constant and m equal to 0, that is a solution of this equation, right? It won't revolve, okay? So then the natural thing to do is linear stability. And if we do linear stability, what one finds is that there's a parameter, there's a region in phase space where it's unstable, the homogeneous solution, and there's some region where it's stable. Okay, so this is linear stability, and from doing this linear stability gives us what is known as the spinodal curve. Okay, so the parameter, the only parameters that are relevant are the overall density. This is the total number of particles divided by the lattice size. So this is the density, and this is the Peclet number, right, which is kind of a measure of the activity. Okay, so in this region, this solid line is the spinodal line, and the region inside, here linear stability indicates that the homogeneous phase is unstable, while outside it's stable. Okay, so so inside, if we start with any like density kind of somewhere here and Peclet number here, immediately we'll get this phase segregation, while outside we'll always get a homogeneous phase. Okay, now so now one can ask so supposing I start somewhere here, I will phase segregate, and I'll get a high density and low density region. Now I can ask, what are those two densities, right? So that is given by what is known as a bimodal analysis, and that gives a bimodal curve. So this is the bimodal curve which I'll discuss now. But basically it says that if I start from this parameter value, I will phase segregate into two densities, high density which has this value, the dashed line here, and low density which is this value. Okay, so this is this dashed line, this is the binodal line. Okay, so this is exactly what Sanjay also talked about in the context of equilibrium phase transitions, and here we have a very similar curve. Okay. So in this case, actually, we can get both this. So this the spinodal line is just from linear stability of this equation. We get this line, and the binodal line, I'll discuss how to get this. This is slightly more non-trivial. Okay. Okay. So the okay. So any questions? No. Yeah.
Now I ask then. So after all, with the two lanes, aren't you effectively introducing?
Yeah. Yeah.
So if you compare with the equation that Solon and company derived, can you make a one-to-one comparison?
Yeah. So like I said, this equation, there are some terms which are slightly different. The first equation is exactly the same as what they had. The second equation is slightly different. The spinodal curve is also exactly the same, right? Yeah. Okay. So okay. So anyway, I will talk about the now this binodal line. How do we get it? So basically, what one has to do is we have to just solve this equation. So if I set this equal to 0 and this equal to 0, then I have two equations, and from that, what are the possible solutions? Okay. So okay. So this binodal analysis goes like this. Okay. So these are the two equations we have, and if we say del T rho equal to 0, then we can solve for m in terms of rho, just this equation. So we get m equal to this, and which we can write like this, right? Del x of. Okay. Now we set del T m equal to 0 and use this value of m in this equation. Then it's clear that we'll just get one equation in the density, right? And this equation, so if we, I mean, after some algebra, it turns out that you can write it in this particular form. It's just del x g equal to 0. Okay. So del T m equal to 0 just gives this del x g equal to 0, where this function g involves some function g naught of rho of, and then there are some gradient square and a second derivative term. Okay. So okay. So this function g naught rho is looks like this, and then there are these other functions lambda, and this kappa is just some constant, and lambda is this function. Okay. So now we have to try to understand the solution of this equation delta x del x g equal to 0 in the steady state. Okay. So so one just sort of interesting point is that this function, if we take if we look at g naught prime equal to 0, this also gives the yeah. Yeah. Oh, right. Yeah. I'm setting the current to 0. Right. Yeah. I mean, okay, in the steady state, there are no particle currents, right? I mean, so that's just the particle current. There's no particle current. Yeah, it's not a non-equilibrium steady. I mean, in that, okay, it's a non-equilibrium steady state with no current, right? Yeah. Okay. Right here. So now this gives the spinal. So now how do we get solve this this equation? Okay, so so in the coexisting phase, I mean, like we have high low density and high density as a function of x. It goes like this. So now if we like integrate this equation across this boundary, then we should have g is a constant, right, across this domain, across this boundary between the two phases. So I mean, so therefore, using this fact, one finds that you can get two sort of equations. One is just this G naught rho should be equal in the low density and high density regions, and then you can construct another sort of constant function which stays constant across the domain. Okay, so okay, and this function has this form. It's a new integral. Okay, so this I mean, this way of analyzing this, finding the bimodal line, and by solving this equation was discussed in this paper, and we followed this approach. So this equation is easy to understand because it just says that the yeah, this equation is kind of easier to understand. This equation, I don't have a good physical understanding of this equation. I mean, it's some sort of nice technique that that's introduced in this paper to find a new integral as you cross this line. Okay, and somehow this gives this equation. So we have two equations and two unknowns. These are the two densities in the low density and high density phases. Yeah, H0 is this function. Okay, so G is this, G naught is this function of density. H naught is a different function, and it just comes from some construction that is described in this paper. Okay. Okay, I don't know if Sanjib has a good understanding, physical understanding of this. I mean, but yeah. I mean, it just comes from doing some manipulations, and we get these two equations. Okay, now you can solve these two equations, and then we get the densities corresponding to the high density phase and low density phase.
So generalization of the double tangent.
Yeah, exactly. In equilibrium, there's a physical way to understand this. It's exactly the double, but in this non-equilibrium case, it's not clear what physically it means. Right? Okay, so this then we numerically solve these equations, and this gives us the bimodal line. And okay, so this is the final. Oh. Okay, so this is the final phase diagram that I already discussed. This is the spinodal line, and this is the binodal line, and this is what we from simulations. These points are from simulations. Okay, so you can see it agrees extremely well with the Monte Carlo simulations. Okay, in these plots we show like here. This is also something Sanjay showed. Like if you look at the distribution of densities, then it's two peaked here and single peak out here. Okay, the other thing that we also did is just look at fluctuating hydrodynamics. So this was also done by Yariv and other people. Okay, so so in this case, one can show that the noise has this form. And one knows this sort of the noise-noise correlation matrix exactly. So what we did is, like, once you have these equations, the simplest thing one can do is just linearize these equations and calculate correlation functions. So we computed equal time correlations, and so these are just exponential. I mean, so it's just short range correlations. And we know this exactly, okay, these correlations. And what is interesting is, so this is of course in the homogeneous phase we calculate these correlations, and this correlation length actually this diverges as you approach the transition point. Okay, so sorry, yeah, as you approach the transition line. Okay, so out here this dot dashed line is it actually gives the line where, sorry, not the correlation length, but this prefactor. The prefactor actually diverges, and so then this kind of
Correlation length, because it would be interesting to find something which looks like.
right, yeah, no, so actually, yeah, the correlation length doesn't do anything, right, yeah, but just the prefactor kind of diverges, right, yeah. Yeah. Okay, so here again we see that there's very good agreement from this linearized hydrodynamics and simulations for the equilibrium correlations. So something we have not done is looking at two-time correlations, but I think it should be probably diffusive because there's no bias, so there's no currents in the system, so presumably it should just be diffusive correlations. Okay, so so we have done this in higher dimensions. You can write the hydrodynamic equations and so on, which the hydrodynamic equations look kind of different from what Sanjay showed. But this is like in the MIPS phase, you see something like this. One interesting thing we observed is that you get this kind of big holes, which also I think is there in some of the continuum models. Okay, so yeah, so there are a lot of interesting questions out here, which we have not analyzed much. Okay, so now let me again come back to this question of this quasi 1D versus if you did this model on exact 1D. So like I said, if you do the exact 1D case without this exchange process, then things don't work. Okay, so supposing you don't put that exchange process and you are doing strictly 1D, then even in the homogeneous phase, if you look at trajectories, space-time plots, it looks like this. Okay, while on the two-lane model, it looks like this. Okay, so they are completely different. Okay, and one thing we notice is that there are kind of this microclusters which stay for long times and then break up and so on in this purely 1D model. Okay, so we think that I mean this formation of this long-lived microclusters is possibly somehow you don't get local equilibrium and so on, and this is the reason hydrodynamics completely breaks down in this case. While in the two-lane case, so here we are just looking at one of the lanes, and you see that it's very well mixed and so on, right? Okay, so it's completely different if you look at the space-time trajectories. Okay, so yeah, like I said, it's okay. So basically, I talked about a very simple lattice model of interacting active particles, and this is a model where you can actually derive hydrodynamics from microscopics and make very detailed comparisons with the microscopic model for even like short time, long time evolution, and we show very good agreement between the two. So we did a detailed analysis of the MIPS transition, and we can predict the spinodal and bimodal curves. Then we can derive fluctuating hydrodynamics. So the derivation is using this Martin-Sigia-Rose formalism, and you can get like all the noise correlations exactly. And then this is a sort of very interesting question, this failure of hydrodynamics in 1D. And I think like similar, there have been other examples where similar failure has been observed. So one recent work is with like Gregory has been involved, where they looked at again run and tumble particles in the continuum with sort of log interaction, okay, and in a trap. So in this case, what they observed is that if you allow interactions between plus and minus particles, then you find that when they try to do Dean-Kawasaki equations, it doesn't work so well. But if you allow the plus-minus particles to go through, then it works quite well. Okay, so I think it's a similar reason, and I mean we studied another model where we also observed very similar effects. So whenever these plus-minus particles are not allowed to cross, then somehow the hydrodynamics description fails. Even though I mean there's always they're anyway tumbling, right? So there's no it's not like there's some loss of ergodicity. but somehow it breaks. So this is, I think, a sort of an interesting question. No. So the interaction is log interaction, and we also tried 1 over r square interaction. That's with that, I think, at least that's what.
We tried it to interact with particles to observe laning transmissions.
Okay.
What process prevails?
In 2D it's okay. So in 2D, actually, I mean, everything works fine, but strictly in 1D there's a problem.
So what if you allow exchange only one way, like plus minus can go become minus plus, but not the other way?
Yeah, I think that's what you guys know. Okay, you did slightly different, but yeah, I mean, we haven't tried. I mean, it's hard to say.
Any further questions? I guess we sort of, yeah, you did say it, I did, but
Yeah, yes, I
guess,
think
okay.
that's it.
Okay.
Yeah.
Last, yeah.
No, I didn't understand. Hydrodynamics fail, I mean, what will you do?
No, if you can write the hydrodynamic equations making the same set of approximations, you will get some equations, right? Now, for example, the hydrodynamic equation still predicts that you will get a MIPS transition, but if you do the simulation, you never get it's always homogeneous.
No, I mean, then I would say that probably we have not found the right hydrodynamics.
Yeah, so I mean, okay, yeah, that is another way of saying, like the hydrodynamics will involve more more complicated, but at least the hydrodynamics based on local equilibrium and product measure doesn't work. Yeah, that's what. Yeah.
Yes. In fact, I have a similar question. In the model of Erignou, Bodino, and so on,
Yeah.
they are mathematicians, so they prove the hydrodynamic limit. Probably, no, it's a proof, or
At least in this
Mathematical
paper, I don't
proof.
see the proof. Like you're saying for their model
yes,
with the exchange.
yes, with the exchange, I think there is mathematical proof.
Yeah.
And
With the exchange, of course, it works. There's no problem.
okay,
Right.
and if you get the exchange, okay, so
Yeah. If there's no exchange, then there's a problem.
so even at the mathematical level, there is a problem.
Yeah.
Okay.
Yeah.
Okay. Yeah, my question was that in their model where they have proofs, they can probably trace back the failure of hydrodynamics at the mathematical level.
Yeah. No.
Well, yeah, but if they cut the exchange, something at the mathematical level should fail.
That they did not study. I mean, if you cut the exchange,
Why didn't study it?
introduce the exchange so that hydrodynamics.
Okay.
Yeah.
So
Yeah,
somehow,
yes.
somewhere at the
No. So.
Okay.
Yeah, it's I mean, more a comment. I mean, thank you very much, Abhishek. It's more a comment. I mean, so if you do the hydrodynamics using this Dean Kawasaki, what you indeed find is that if the particles cannot cross, basically, I mean, when you do Dean Kawasaki, you have to basically approximate the 2-point function by the product of the 1 point to close the equations, and this doesn't work simply when you have this non-crossing condition. And that's why at least the Dean Kawasaki doesn't work. I mean,
Right, yeah.
it's rather clear
Yeah.
why.
It might
So
be
if you have a
possible
soft potential where the particles can cross, this is still fine. Yeah, this is perfectly fine. So that was the other comment. Even in 1D, if you have a potential, but if they can cross, then it's perfectly fine. But if you forbid this, then you are facing this problem. At least in the Dean Kawasaki approach, I don't know in the general hydrodynamics, I don't know exactly what it means, but for Dean Kawasaki, this is what happens. You cannot.
Right, yeah.
Yeah, exactly. So if you have that, then you cannot use Dean Kawasaki.
Thanks so much, Abhishek, for a very stimulating and the discussion, of course, will continue over coffee. Yeah. Next speakers, Somrita Ray. Yeah.
Okay, so good afternoon all. Am I audible? I hope. Okay. So thanks for joining me today, and I'm very pleased to be here, and thanks to Professor Sabhapandit for inviting me. And I'm very excited because I'm giving talk to an audience. Some of the people here are